So the area between two curves can be represented by a double integral, and a 1 is the integrand. So that's going to be like a quiz question. It's going to be a test question. I could make it a true-false question. All sorts of different possibilities. You need to make sure that you get that. If there's something other than a 1 in your double integral right there, that means it no longer represents area between two curves. Well, what does it mean? There's lots of possibilities, and we'll hopefully have time to get into that today if we get through enough examples. Okay, now when you're doing area between two curves, I hope that you remember from Calculus 1, there were two cases. One where you're integrating with respect to x, and the other one where you were integrating with respect to y, which is harder for the calculus. When I teach Calculus 1, they always hate those because most of us like to think in functions of x. So let me just remind you, here's the two pictures, and we have to worry about that also in this class. It's not going away. So if you have a type of problem where you're finding the area between two curves, and you have a function of x here and a function of x here, and the area between your two curves is what we call vertically simple. So we have a vertically simple region. Then the area, if you were doing this as a Calculus 1 problem, you would have a taller minus shorter, like so. So this is the Calculus 1 version. But for us, you know, we did a little bit of this derivation last time. You're going to have a double integral representing the region, and the outermost variable of integration is with respect to x, and the inner integral is with respect to y. And so notice the inner integral, the shorter function is the lower limit, and the taller function is the upper limit. And this rectangle that you see here is known as a representative rectangle, which can be used to help you figure out the limits if you're having to iterate the integral on your own. So the order of integration is going to be important when you're doing these integrals, because the alternate way is where your order of integration is dx dy. What does that mean? That means that the region of integration is going to be kind of sideways here. So here you have a function of y. So this would be some function of y. X is equal to, say, h2 of y. And then this guy over here, x is equal to h1 of y. So those are functions of y. And so you can kind of think of, if you were doing this as a Calc 1 problem and you were asked to find the area between these two curves, your area, oops, not a double integral, sorry. Calculus 1 people don't know how to do double integrals. So your area would be going from C to D, that's on the y-axis. And instead of taller minus shorter, you would have rightmost minus leftmost. And this is important, not taller minus shorter. You would have the rightmost function, which is h2 of y, minus the leftmost function. And you would integrate with respect to y. And then if you rewrote this as a double integral, where this integrand is written as an integral itself, that is the same as this double integral. So notice the order of integration is dx dy. And the representative rectangle is sideways. The representative rectangle is written sideways. Now, when you're drawing a representative rectangle, and some of you are like, I don't need no representative rectangle, that's dumb. Yeah, you are, because sometimes your region is a little tricky, and if you draw one of these in there, it helps you out. But what I do, instead of drawing a representative rectangle, just to make it a little bit more fun and also easier to make sure my brain thinks, is I put a little man in there. So if you're doing a region that's vertically simple, which is this region here, your little man or your representative rectangle is drawn vertically. So the upper limit is where his head is touching, and the lower limit is the function that his feet are standing on. If you're dealing with what's known as a horizontally simple region, that's this guy here, if you're going to draw your little man, you have to draw him where his head is to the right and his legs and feet are to the left. This is important because your upper limit, your rightmost function, is where the little man who's now drawn sideways, that's your representative rectangle horizontal there, that's the rightmost limit, and his feet are standing on the lower limit of integration for the innermost integral. This is important that you get that. You can use your little man. So if your area is your region of integration is given to you in set notation, which sometimes it might be where x is going from some pure number to some other pure number, and y is going from a lower function to an upper function, your area is going to be a double integral where dy dx is your order of integration. And remember, the outer integral always is only allowed to have pure numbers on it. Well, that was one of the rules we left you with last time. And the innermost integral has the shorter as the lower limit and the taller as the upper limit. Here, if you're given the region of integration that you're trying to find the area of, the y is going from some pure number to some pure number, and the x is going from lower limit, which is the leftmost graph curve, and the rightmost is the upper. So you're going to have double integral. Your order of integration is going to be dx dy. Y will be going from the pure number c to a pure number d, and x has variable limits. Okay, so these are the two possibilities when you're doing a double integral representing area between two curves. Now, what if all your limits of integration are pure numbers? That can happen. Those type of regions are rectangular. The region of integration is blank, rectangular. Oops, it's in the next blank. Mine got pushed to the next page. Rectangular. Now, I rarely give you rectangular regions of integration just because I like to make mine harder. But let's just look at an easy example here where you obviously have a rectangle as your region, okay? So how would a double integral work if somebody said, hey, set up a double integral representing this area? So if you do it with dy dx, that's the vertically simple choice. If you put your little man in here, there he is, vertical, his head is on this upper taller function, which has the equation y is equal to d, and his feet are on the lower limit, the shorter function, y is equal to c. Those are just horizontal lines, so they have nice equations. So your area here is going to be where x goes from a to b, so those are the limits for x, and the innermost integral has the variable of integration as y, and y is just going from a pure number c to a pure number d. Now, before I actually do this double integral, let's use 5th grade math to actually figure out the area of this rectangle, because we all know how to find areas of rectangles, right? It's length times width. Would you agree?
Yes.
Okay.
Yes.
So how about this is the length right here, this side length here. But what is that? It's the difference between d minus c. Okay. Well, what about the width? Well, that's whatever the measurement of this is, but that's b minus a. So this is the answer without doing any calculus at all. No calculus needed. That's overkill to use calculus to find the area of a rectangle. But in fact, we're gonna do a double integral, and the double integral representing the area of the rectangle is right here. There it is. So let's do this in slow motion. So the innermost integral always has to be done first. So do this first. And then what do you have? Well, what is the antiderivative of 1, because that's understood to be the integrand, with respect to y? So remember,
1.
yeah, good. You're doing the opposite of differentiation. So just y, and you're going to evaluate y going from the limits of c to d. And then after that's done, you'll do the outermost integral. So if you're using the fundamental theorem of calculus, don't forget you have to plug in the upper limit first. And remember, d minus c is just some number because those are constants. Then what? Well, now we're going to integrate with respect to x. And since this is just some number, like 5 or whatever, what is the antiderivative of 5 with respect to x?
5x.
5x, yeah. So you'll just have the constant times x, and x is going to go from the lower limit of a to the upper limit of b. And then you use your fundamental theorem, and we're done. And of course, these are the same. So I just wanted to show you that even though it is overkill, you can use a double integral to represent the area of a rectangle. And the other thing, takeaway I want you to get from this example, if all your limits are constants, if all of the limits are pure numbers, the region of integration is understood to be a rectangle. So that's good to know. Good true false question. Now let's do something a little bit more interesting than a rectangular region. So I want you to consider this example, which a Calculus 1 student could do, because it's area between curves, but we're going to do it the Calculus 3 way, okay? So be careful, like on one of these quizzes, not your midterm, of course, but if I say, hey, come up with the area of this region bounded by these two curves on your handwritten work, I want to see the Calc 3 method, the double integral, not the single integral from Calc 1. Otherwise, I'll take away all your points. So it's not that hard. If we were to graph this, if you graph sine of x, okay. So there's pi roughly. So that's sine of x. If I graph cosine of x, all right, gotta make sure I get this right. Something like that. So there's cosine. And they're giving me the limits. So they're saying right here, they're supposed to intersect like here at pi fourths. And the other intersection turns out to be 5 pi fourths, right? Oops, right there. So they're telling me, they're giving me a lot of information, so I don't have to do too much work. So the area, if I use a double integral, not a single integral, because that would be the Calculus 1 method, I want to go double, double. And I'm going to use the vertical simple choice. So that means my order of integration is going to be dy dx, which is my personal favorite, because that means we can all think in terms of functions of x instead of functions of y, which is a little trickier. And the integrand is going to be a 1, because that's what it is for area. So what are the limits? I'll give you a hint. The outermost limits for the outermost integral, one of the rules are those have to be pure numbers. So, and this is with respect to x. So look at this region, and what pure number is x going from what to what?
Pi fourths to 5 pi fourths.
Yeah, they gave it to you. That was awfully generous. It was pi fourths to 5 pi fourths. So you didn't have to think much there. But what about the limits for the innermost integral, which is the integral with respect to y? What is y doing on this integral? And if I draw a little man, I mean, I don't have to draw the little man, but there he is. He's being drawn vertically. His head is touching the upper limit, which is what?
1.
Well, what is this graph of? What is this graph of? Not 1, but
Sin x.
it's variable. I know the highest it can get is 1. That's true. But it's variable because if I move the little man over a little bit, like let's say I put the little man over here, just say, whoop. Do you see how that's a variable upper limit there because of it can swing around depending on where I move my arbitrary little man?
Yes.
It's not going to be a pure number. It's not constant. So it's sine of x. So the upper limit for y is a variable and it's sine of x. And that should make sense because that's the taller function. And so that's going to be the upper limit. Now the little man's feet are resting on the lower limit, which is also variable, which is?
Cosine x.
Thank you. Thank you, Elo. And now we're ready to actually do the integration. So this is sometimes the hard part, is the setup. And if you can't do the setup, then the rest of the problem is going to go down the drain because you'll have it wrong. Some of the issues I see students wrongly, put pure numbers when there shouldn't be pure numbers. Some other issues is sometimes students have these limits backwards. And how do I know it's backwards? Right away, I know it's backwards when the final answer is negative. Because when you're finding area between curves, your final answer has to be a positive number. Well, do all double integrals only have positive results? No, but when you're using them to represent area, they will. And so if you get a negative number, I'm just going to take away all your points because that should have been a red flag to you. And you should have stopped, take a deep breath, and do the problem over again, because you shouldn't be getting a negative number when you're using the double integral to represent area. Okay, so first do the innermost integral. What's the antiderivative of 1 again with respect to y?
Y.
Y.
So I still have to do the outermost integral, so you have good notation. Put that in there still. So you have y, and y is, put his limits on there. Okay, fine. And then plug in that upper limit first, and then minus the lower limit, and then you still have the outermost integral. So let me just put it there. Oh boy. Yeah. And now, did you see that this integral is now a single integral that we have left? And this is actually the calculus 1 formula for the area between those two curves. So you will end up there. So this is how the Calc 1 people would do their setup. And then you go, okay, well, what's the integral of sine? I think it's minus cos. And the integral of cos is sine. And then you're going to evaluate this between pi fourths and 5 pi fourths. And then it's just a matter of, do you know your unit circle from trig and all that other stuff? And I'm just going to do this very quickly. So you got that minus, although this is the part where some students choke. They go, I can't get I know how to do the setup and I know how to integrate, but I don't know how to evaluate. Because I forgot all my trig. Okay. So you're going to end up with minus negative square root of 2 over 2 minus, and I think that's also negative square root of 2 over 2. And then minus, and then here it's going to be negative square root of 2 over 2 minus square root of 2 over 2. And then you add up all that mess together. And I claim you'll get a positive number, and it's going to be 2 square root of 2. So the area between the two curves, between those limits they gave us, is 2 square root of 2. Questions?
I'm good.
I'm fine.
Everybody okay? Yeah. Okay. All right, I'll move on. So let's do an iterated integral that's way harder. Okay.
Should we have asked questions?
No.
Now I'm concerned. There was an odd beat in between.
No, this is pretty straightforward. It should be cut and dry. But the next problem might involve a little issue. Okay. So let's see why and where and all that stuff. So I'm going to do 2 more problems, and then I'm going to put you in breakout rooms and have you try one. And it's going to get a little trickier. So watch closely how it's going to get trickier. In example 3 here, you're being given the double integral, and you're being told, hey, this double integral actually represents area between 2 curves. What is the region of integration looking like? So sketch it based on just that double integral. And then after you've sketched the region, you're going to evaluate it. And then part C is the real tricky part. There's a skill that you're going to need to learn immediately, and you can wait till after midterm 2. I need you to get it immediately, is switching order of integration. And you have to know how to do this because I'm going to be giving lots of problems on it. And it doesn't involve calculus, but it involves a way of thinking of graphs and regions and so on that you should have gotten in a pre-calc and your Calc 1 class. But I find it's missing. There's some gaps, and I'm going to try to fill in those gaps when we do it here. All right, so let's start. I'm going to give you the Raschke idiot-proof method to sketch the region of integration when you're given a double integral. So listen up, because this is key. It's not hard. But a lot of times I'll have students graph the graphs, and then they shade in the wrong region. And then I just take away all their points because they can't figure out the actual region of integration. It's like, Okay, so when you're given your double integral, what I would recommend that you do, if you want to have the idiot-proof method, is write down 4 equations that you're going to graph. What 4 equations? I'm going to show you how to get them. First, let's start with the dy, which corresponds to the outermost integral in this case. So you're going to write the equation y equals 0, and then for the upper limit, y equals 2, and we're going to actually graph those two curves, which are very easy because those are just straight lines. And then you're going to look at the innermost integral, and you're going to go, And that innermost integral is with respect to the other variable integration, dx. And so you're going to go, You're going to write this equation. You're going to go x equals y squared, and then for the upper limit, x equals 4. And then you're going to graph these 4 equations. And you can think of all 4 of these graphs as being fences around your vegetable garden that you're growing. And your job is to identify the vegetable garden and shade it in. And believe me, it seems like it's real easy, but students choke on this, and then the rest of their problem goes down the toilet because they couldn't really identify their region of integration. And this is going to happen like for the rest of the semester, 2 months out. So if you can't identify your vegetable garden, we're in trouble. So first up, when I graph y equals 0 and y equals 2, I claim they're straight lines, but here's the question. Are they vertical or horizontal? I'll check the chat.
That's a vertical line. Sorry. What was it?
Horizontal
Y
line.
equals 2?
Y equals 0
Oh, that's horizontal.
and y
That's horizontal.
equals
Yeah.
2.
Horizontal
Those
line.
are both straight lines, but are they vertical or horizontal straight lines?
Horizontal.
They're horizontal.
They're horizontal. Thank you. I get students who can't do that part, so then it goes down the drain. So y equals 0 is simply the horizontal line that lives on top of the x-axis, and y equals 2 is the horizontal line that intersects the y-axis of 2. Boom, I got 2 of them. Now let's draw the other fences around your vegetable garden. Well, x equals 4 is a vertical line, so that's kind of easy. But x equals y squared, now this is a little tricky because it's one of those horizontal parabolas that are opening up to the right. So you have to be kind of careful here. And I claim, if you're real careful about drawing this, because I claim it does intersect that point right there at the 0.42. And there's my horizontal parabola. So now here's the hard part. I got a lot of graphs going on here. What is the region of integration?
The upper half of the parabola.
Yes, you want the vegetable garden to be bounded by y equals 0, y equals 2, x equals 4, and the horizontal parabola. And the only region that's bounded by all 4 of those fences, if you will, is this region here. So you're going to shade in that right there. If you shade in anything else, like you shade in every, like, down here or whatever, you're going to blow it. You don't have the region of integration identified. So that can be tricky. This one wasn't too bad, but wait till you see some more. Okay, now let's evaluate the iterated integral. Okay, that's not hard. If we look at this double integral, we're going to do the innermost integral first. So we're going to integrate with respect to x. Please notice that dx dy is the order of integration, which if you were paying attention to the first part of this lecture when I was identifying who's the vertically simple and who's the horizontally simple, the dx dy is the horizontally simple order of integration choice. Know the difference. So if we're integrating with respect to x first, and the integrand is simply a 1, that's understood, what is the antiderivative of 1 with respect to x?
X.
Just x. So you're going to have x going from the limits of y squared to 4, and you still have the outermost integral. So here, don't forget, evaluate at the upper limit first, minus evaluate it at the lower limit, and then boom, there is the single integral that represents the area between curves. And if this were a calculus 1 problem, which it isn't, and somebody said, hey, give me the area between the, these two curves, you would have come up with that. And then this is easy to integrate for y minus y cubed over 3, and we'll evaluate between 0 and 2, and I just get 16/3. And it is a positive number, and it better be, because this is representing area between curves. Okay, so now the hard part. How do you switch the order of integration? This is a skill that you need for the rest of the semester. Okay, and I'm going to go over it in slow motion. And I don't want to give you the motivation yet because it won't make sense. But within 10 minutes, you'll get the motivation. Okay, I promise. So first of all, what does it mean to switch the order of integration? It means instead of dx dy, I want the integral to be rewritten as dy dx. That's all. Here's how not to do it. Please do not write this down. Oh, well, dy dx, how hard could this be? I'll just, swap these two integral symbols. Okay. Do, 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 la, la, la. Wrong. Well, why is that wrong? Well, it's violating one of the rules and regs that I gave you when we went over the intro the other day. And that is, I think it's rule number 2, that the outer limits of integration must be constants with respect to both variables of integration. So it's like, if you just swap the two integral symbols and keep their limits exactly the same, you've just violated a rule. So this is a meaningless double integral and is not going to be even close to the answer. Not even. Well, then how do you do it? Well, very carefully. So the way you're going to do it is you're going to acknowledge, first of all, that definitely we do need a dy dx going on there. Then, since dy dx is the vertically simple region, when you draw your little man in the region, you can draw him vertically. So there's your little man standing up in your region. Let's do the outer integral limits first, because those have to be pure numbers. So if you look at our vegetable garden here, this is the shaded region. What are the limits of x? What pure number to what pure number is x doing on that region? Should be pretty easy to see.
4 zeros.
Okay, so the lower limit is what? 0. And the upper limit is?
4.
Yeah. That was easy. Now what? Well, even though y is going from 0 to 2, if you put 0 to 2 on there, no. This region is not rectangular, so the limits are not all pure numbers. It's clearly not rectangular, so you got to be careful. So the little man's feet are standing on the lower limit for y, and notice they're standing on the x-axis, which has the equation y equals 0. So the lower limit for y is y equals 0. The upper limit is variable because the little man's head is touching this upper half of the horizontal parabola. Is that clear? So this limit has to be variable. If you put a pure number there, you're dead. Well, what is it? Well, you have to be careful. Let me show you what not to put there. If you're like, oh, remember this horizontal parabola had the equation x equals y squared. So I'll just, put y squared here and I'm good to go. No, you're not. You just violated one of the rules and regs of double integrals, where I mentioned that the limit of integration cannot be matching the same as your variable of integration. In other words, since we're integrating this most integral with respect to y, you're not allowed to have any y's on the limits. That's like, But then what? Well, you still want to say that the upper limit is that horizontal parabola, but what you're going to need to do is you're going to need to solve x equals y squared for y. So I'll square root both sides. And what do you have to remember when you square root both sides of an equation? Somebody tell me.
Plus or minus.
Thank you. So we have that y is equal to plus or minus square root of x. And which one is it? Don't put both. I hope you noticed that the upper part of that horizontal parabola would have the graph of y equals square root of x, and the under half, which we're not using as part of our region, the negative square root of x, is the lower half. So we want the upper half. So we want our upper limit for y to be positive square root of x. Now we're ready to evaluate this new integral, which still represents the area of the region. So we better get the same answer 16/3 as we did when we did part B. And we will, but it's going to look a little different. So if I integrate with respect to y, the antiderivative of 1 with respect to y is just y. And we're going to have the limit 0 to square root of x. And we still have the outermost integral. And so you're going to just keep going here. And okay, fine. And then you're just going to evaluate what's the square root of x's integral. Okay, I think it's 2/3 x to the 3/2. You're going to evaluate between 0 and 4, and you'll get 4/3, and minus 0, you won't care. You be careful here. This is the same as the square root of 4 cubed, which is 2 cubed, which is 8. So you're going to have 2/3 times 8, but that's 16/3. And we knew that was going to be 16/3 because they have to match. You better get the same answer. Okay, and we're done with that example. Questions?
I'm good.
I like this meme because it applies to the problem that I did up here.
Right, quick question.
when
Okay, so like, what would be a situation where you would actually have to physically like switch to whatever integration and not just be a gratuity of the math like problem?
my internet just died. I'm going to have one of those days. I apologize. Can you guys hear me okay?
I hear
I
you.
thought it was me,
Yeah.
to be honest. Yeah. But
Yeah, because your internet is messed up, right, Nick? So it could have been your internet. I claim it's Nick's internet that messed up my internet.
don't pin that on me. Come on.
I mean, assuming this entire like is entirely local to Nick's like house, maybe.
Yeah, Nick, I think your house internet problems is messing with my internet. Thanks a lot. I'm going to charge you some money for that.
These double integrals are
Thanks.
killing my Wi-Fi. I'm sorry.
They're killing mine too. No, sorry. Okay, so where were we? The meme was that I just showed you had to do with this example I did where I tricked us into doing the integration for just finding the area of a rectangle. We didn't really need to have a double integral because we just showed that we just did length times width. But I tricked us into doing it. So that's why that meme is supposed to be cute. If you didn't laugh, you're not having enough fun in my class. Come on. Okay, so did somebody have a question? I think right before my internet died, somebody said, oh yeah, I have a question.
This is Dave.
Oh yeah, I had a question.
What are you talking about, David?
Like the double when you're next to each other, they resemble something really unfortunate. Is this just
Oh.
me?
Yeah, I don't know. I don't see it, but maybe talk to me later in my office hours. Okay.
It's an entirely immature joke. Okay, but anyways,
Nicholas
so
Gonzalez has a question for God. Why? Yeah, well, that's an existential question. And who's really good at answering existential questions? He's right here in the class. That would be David.
you'll have to ask Max Mofo.
While we're here, and maybe my internet's slow because I'm on the internet, so I may kill this off, but I wanted you to see where we are in the course. We're finishing up week 8 here, and then next week starts week 9, which is you're going to have your midterm, and then we'll do some more chapter 16 material. Okay, so and keep calm and pass calculus 3. All right, that's the hope, right?
Yes, ma'am.
You guys still out there?
Oh yeah, we're here. Mm-hmm.
We trying.
Now, if you don't pass my class, which would be sad, but here's some good news. I'm teaching the class again next semester, so welcome back. And if you don't want to take me again, I understand.
If we do all pass the class, do you mind teaching DiffyQ?
I appreciate the vote of confidence, David, but it's already been decided. The schedule is done, and I didn't request DiffyQ again. I love teaching DiffyQ, but because I knew we were going to be remote again, I wanted to keep my schedule a little bit easier for me. And teaching DiffyQ,
Right.
love it, but it takes a lot of my time and effort and work. But here's my open invitation to you, David, if you do plan on taking it. And this is for the rest of the class as well. Everybody listen up. How many people here are planning on taking Math 253 next semester? Okay, you can do the chat also. Go for it. Okay, I know David is. Who else besides David is taking Math 253? Anybody?
2.
Okay, George is. Adriana, she says if I pass. Possibly Anthony, Lizette, Jocelyn. Okay, Nick, Jordan. Wow. Okay, quite a few folks are going to move on to Math 253. Okay, great. Like I said, differential equations is God's gift to electrical engineers. Okay. Yeah, you probably should take linear before you take differential equations. I would recommend it. But if you're not planning on doing that, fine. So my open invitation, first of all, I want to say, if you're going to take differential equations, they have a little joke. It's not really a joke. The cliche for calculus is if you really want to learn algebra, take calculus. The other cliche, if you really want to see if you know your calculus, take differential equations, which is very true. You got to know your calculus cold. But you also have to be good at algebra also, because there's a lot of factoring of polynomials in there. There's a lot of work with complex numbers from pre-calc. So that, which I think is fun, but some people may not find it. It's fun. But the thing is, you know, if you want to get some help or support, come to my office hours. And what are they? Well, email me and I'll send you my Zoom links for next semester's office hours. And come on in. I'd love to answer differential equations questions. They're a blast. Okay, so that's my open invitation to all of you. Okay, I'll see you next semester. Okay. Given the iterated integral, which is this, I'm going to do this problem and then you're going to do the next one. So pay attention because I'm going to put you in breakout rooms soon. Do you notice that the integrand is not a 1?
Yes.
That means that this is not, this double integral does not represent the area between two curves. Okay. What does it represent? It could be a lot of things. Since they're not telling us, who cares? Okay, I'm just saying. You'll find out soon enough what that means, okay? Be patient. But you still can do the double integral, even though it's not a 1 there. You don't have to know what it represents in order to do business with it. So let's, so that means not an area, not represented. But here's the deal. We still can talk about the region of integration, which is still going to be the area between two curves. So you need to still go graph that puppy. So you're going to use the Raschke method that I've already taught you, and I'm going to go over it again in case you fell asleep in my last example. The outermost integral is with respect to x, and so if you look at the outermost integral's limits, write down the equations x equals 4, x equals 0. The innermost integral is with respect to y, so write down these next two equations, y equals 2, y equals square root of x. And then graph all 4 of these curves. And then, remember, these represent like the fences around your backyard vegetable garden. You have to identify the actual vegetable garden and shade it in. So x equals 4 and x equals 0 are beautiful vertical lines. There they are. Y equals 2 is a horizontal line. There he is. And y equals square root of x is the square root function, which looks like that. You got to be careful drawing it because he actually does intersect at this point 4, 2. Okay, fantastic. What do I shade in? Does anybody have an idea of what I actually, by the way, if you don't shade in for me, I don't give you full credit.
It's like that right triangle.
Yeah. The right
Is it-
triangle whose hypotenuse is like x.
Curvy
That one.
hypotenuse, right?
Yeah.
There's your vegetable garden right there. Okay. Fantastic. Now, the dy dx, the order of integration that they are using is the vertically simple choice, just so you know. And so we're done with part A. What's next for part B? Oh, we were supposed to answer a question for part B, which I think I already answered, but let's just try it again. Why isn't this integral an integral that represents the area between two curves? Why isn't it?
The integrand is a
Doesn't
1.
equal 1.
Yeah, the integrand does not equal 1. Very good. You guys are doing great. So it represents something else And I can't tell you what the something else is. That's secret information, secret squirrel information for now. Okay, why is it impossible to evaluate the iterated integral, that's fancy schmancy talk for a multiple integral, in this case a double one, as it stands right now? Well, what do you mean? Let's just look here. Let's pretend we didn't know that we couldn't integrate. Like, let's say somebody said integrate, and you're like, okay, no problem. Let's take a look. So the innermost integral is with respect to y. Okay, fine. Do you know how you're going to integrate 3 over 2 plus y cubed with respect to y? Don't say u sub. It ain't going to fly. Like, try it. What's your u and what's your du?
It'd be 3y squared, or actually u is 2 plus y cubed.
Okay.
And
If that's
du
the
is
case, then what would your du be?
3y squared.
Do you
2y.
see a 3y squared in the integrand right now? I don't.
No.
Absolutely not.
I don't. No way. Won't work. Sorry. Can you see brick wall? You just ran into one. Well, now what? Don't do what my beginning algebra students do when they can't do a problem. They just simply write, no solutions. That's a good one. Nice try. But here's the thing that I want you to get right now. So this is the key. Now I'm going to answer the question, why do you have to know how to switch the order of integration? Which I made us do back here, you know, just because I said switch the order of integration. It wasn't clear why. And I just said, hey, it's a skill that you need. Hey, folks, you better know how. Well, now I'm going to give you the motivation. Welcome. You may run into a double integral like this one that's not integrable as it stands right now. Not even if you, use any of the advanced integration techniques from Calculus 2. You know, integration by parts won't work. None of that. You're stuck. Well, what to do? What to do is you're going to switch the order of integration. And the beauty is going to be it then will be integrable. Because folks, I hope you can see that if when I switch the order of integration, the integrand stays the same. That doesn't switch. But the dy dx will flip. So it'll be dx dy instead. And so that means the innermost integral will be with respect to x. And when we integrate 3 over 2 plus y cubed with respect to x, that entire quotient looks like a constant multiple. Woohoo! And you guys know how to integrate a constant with respect to x, don't you? Say yes.
Yeah.
Yes.
Sure you do. Come on, you learned that in Calc 1. So why is it impossible to evaluate? Because no integration technique will work. You know, nothing will work. U sub won't work, nothing. You're stuck. So the key is going to be this. Once we switch the order of integration, it will be integrable. So we're still going to have the double integral. The integrand stays the same. Don't be switching him around or replacing x's with y's or do any nonsense like that. It remains unchanged. The thing that's going to change is we're going to have the order of integration change. We're going to do dx dy instead of the original dy dx. Now keep in mind, this is the horizontally simple choice of integration, and that's going to be key once we put limits on these integrals. So we're going to need to do that right now. We're going to iterate it. Iterate is the fancy verb for stick the limits on the integral symbols. Okay. All right, so let's do the easy integral first, the one that's going to have pure numbers. So the outermost integral, which is with respect to y, is going to have some pure numbers here and here. Well, what pure numbers? Well, go look at the region of integration right here. And look what y is doing. Look on the y-axis and try to see what's the lowest pure number that y hits on the region and the highest pure number. This should be obvious. What are they?
0 and 2.
Very good. 0 and 2. Pure numbers. Y is going from 0 to 2. So what's x doing? Well, since this is the horizontally simple region of integration, and please don't say 0 to 4, okay? I'm gonna have to wring your neck. It means you didn't listen. The limits are all pure numbers, only if your region is rectangular. And this region ain't rectangular, so not all your limits are gonna be pure numbers. Since this is the horizontally simple choice for order of integration, I'm gonna put my little man in there, and he has to be drawn horizontally. And his head always has to be to the right. Please don't draw him backwards. So there's my little man. This is going to help us. The little man's going to help us. The little man's feet look like, no matter where I arbitrarily move my little man up or down, his feet look like they're always going to be firmly planted on the y-axis. But that has the equation x equals what?
0.
0.
So the lower limit of integration for this, for x, is 0. Now, what about the upper limit? Well, that could be variable, because I could slide the little man a little further up, you know, like up here instead. Woo! And so that kind of varied a little bit. But his head is still going to be touching that curve, which has the equation y equals square root of x. So it's going to turn out that variable limit is going to be, excuse me, yeah, this is wrong. It's this, but it's wrong. Why is it wrong to put square root of x on the limit, even though in fact the little man's head is resting on that curve, which has the equation y equals square root of x?
You
It
mean
has the
in
same
respect
variable.
to y?
Yeah, I'm violating one of the rules of integration when you put the limits on. The limit can't match the variable of integration, right? So, and David, they'll think that you're really smart. I actually
Double check
didn't
this out,
invent I didn't invent the little man. I stole it from either Patrick JMT or Math is Power for You. It's from one of those videos, and I thought it was a genius way of looking at things. So what you're going to need to do is you're going to need to solve y equals square root of x for x. So you have x equals something. Well, that's not too hard, right? What am I going to do to both sides? Square both sides. Now, when I square both sides of an equation, do I need the plus or minus?
No.
No, only when you take an even root. So now I get x equals y squared. So I'm like, oh, okay. So my upper limit of integration is going to be x
Y squared.
equals y squared. Now this is okay. And I just switched the order of integration. Yay, success. And now good news, people. This is so awesome. It's integrable. We can do it. Yeah, because we're going to integrate with respect to x, and this just looks like a constant because we're holding y constant when we integrate with respect to x. So that entire quotient, 3 over 2 plus y cubed, just looks like a constant, like 10. And so you know the integral of 10 with respect to x is just the constant, whatever it is, times x. And x is going from 0 to y squared. And please continue to write down, copy down the outermost integral, so that when I read your work, I know you know that I know that I know that you know that you know that I know that I know that you know that there's still an outermost integral left to be done, right? Okay, so then when I use my fundamental theorem, which says first plug in my upper limit and then do the lower limit, I'm still going to have this outermost integral and my constant, and then I'll have y squared minus 0, but that's just y squared. So my last thing I have to do is now a calculus 1 problem, and any calculus 1 student can do this single integral problem, right? What rule of integration do I use? And please don't say use sub, because that's a technique, not a rule. I'll give you some choices. Power rule, exponential rule, arctan rule, log rule, arc
Partial
sine rule,
fraction decomp.
partial fraction decomp. Oh my
I don't think you
goodness.
have to, no.
Log.
Oh, wait, no, no.
Oh my goodness. Well, you could factor 2 plus y cubed. It is a sum of cubes, but I don't think you need to go that route because I think it's easier than that.
Use the power rule.
Log rule.
Rule is correct. I claim this does have the look of 1 over u du, which then has an antiderivative ln absolute value of u. So when you do these, I'd like you to tell me the u and the du. Otherwise, I will not give you full credit. I'm going to take away a lot of points. Well, I know how to do that in my head. That's nice. Write it down on your paper. Okay. Otherwise, I'm going to think you're cheating. A lot of these apps that we're finding that are cheating apps, I've been talking to my colleagues. We've been having meetings about the amazing amounts of cheating that's going on these days. And of course, present company exempted, right?
Yeah, that's right.
The U and the DU, apparently a lot of these apps that do all the work and whatever, they don't always show the U, the DU, and the A and all that good stuff. And, you know, they skip steps. And so be on the lookout for skip steps. So I've been doing that a lot. Like my Calc 2 students, they skip steps all the time. And I know it's not them. They're just copying something down. It's scary. Okay. So what's the U and the DU for this log rule? Quick.
2 plus y cubed
Mhm.
and 3y squared dy.
Mm-hmm. Good. So this already has the look of 1 over u du. So the result is going to be, you know, ln of u, and you're going to put your u back in. I'm going to back substitute the 2 plus y cubed, and then my limits are 0 to 2, and I'm going to get some weird answer, but that's okay. So I'm going to have ln of 2 plus 2 cubed, so that's going to be something, minus ln of 2 plus 0 cubed. Okay, fine. So this looks like it's going to be ln of 10, that's just some number, minus ln of 2. And you're pretty much done, but it'd be nice if you went one more step just to be cute, because you can condense these two logs into one log, right? ln of what?
ln of 10 divided by 2 or
Mhm.
5 or
What are the names of these apps that be sure not to use? You shouldn't be using any apps. I don't even want to get into it. Yeah, the Briggs, well, they skip steps too on occasion. Yeah, 10 over 2 if you're using one of the log properties, and then that even reduces further to ln of 5. Final answer, ln of 5, and we're done with this problem. So congratulations on looking at a double integral where switching the order of integration was mandatory. So now it's your turn. This one, I'm going to give you an easy one, though, and I'm going to put you in breakout rooms. This one does represent the area between two curves. How can I tell? What's the key giveaway?
The integrand's 1.
Good. The integrand's 1. So it does represent the area between two curves. And you're going to actually get to figure out what that region is, because you're going to sketch the region of integration as the very first thing you do. Then you're going to evaluate the iterated integral. And finally, you and your buddy are going to switch the order of integration. And hopefully that answer is the same as part B. Otherwise, you're in trouble. Okay, so we've got 25 people in the room. How wonderful is that? We got full participation. Oops, I don't want to go too far here. Let's do, yeah, I think that will work. So once I create the room and you get invited to your room, go in there and we'll see you soon. Bye. Have fun. So here's what I hope that you gleaned from doing this example with your buddies. When you graph y,
share your
yeah.
screen.
Sure.
my screen. Yeah. You're right. It always ends up not sharing. I apologize. Let me do that now. Okay. So you're going to do the Raschke method, which is idiot proof. So don't blow this, okay? You look at your integral and you go, oh, I have to write down 4 equations. Y equals 0, y equals 1, x equals the cube root of y, and x equals y squared. You have to graph all 4 of those. Well, y equals 0 and y equals 1 are easy because those are just horizontal lines, right? So what could go wrong? Well, these 2 equations are given to you as functions of y. So it's a little bit tricky because most of us like to think in terms of functions of x, and so does our graphing calculator. But x equals y squared is a horizontal parabola, so maybe you can get that one on your own. But the other one, you may want to like cube both sides so that you can rewrite it. And when you rewrite it, you get y equals x cubed, and that's easier to graph using your graphing calculator. And when I graph it, assuming my Surface Pro. Now, here's what will happen on your graphing calculator when you graph this. This little sliver, unless you zoom in, is so tiny you might even miss it. Your eyeballs will go, I don't see anything to shade in. Yeah, you are. It's this little region right there. You're just using this integral to find the area of that little tiny region. Cute! So that's the sketching the region of integration. If you evaluated the iterated integral, when you integrate with respect to x first, the antiderivative of 1 with respect to x is x, and then you evaluate at the limits, and then that just means you're going to plug in the cube root of y minus y squared dy. This is just a calculus 1 problem. You have to be careful because when you integrate y to the 1/3, 1/3 plus 1 is y to the 4/3, and dividing out by 4/3 is the same as multiplying by the reciprocal. And then y squared has the antiderivative y cubed over 3. And you're going to go, okay, I'll evaluate this between 0 and 1, and I get 3/4 times 1 to the 4/3 minus 1 cubed over 3, minus 0. And so 3/4 minus 1/3 is what?
5/12.
12.
5/12. Don't give me a decimal result. I want to see fractions, and so does my math lab. Unless they ask you for a decimal, give them a fraction. So did everybody get the 5/12? I hope. All right, now how do you switch the order of integration? Very carefully. So notice that the current order of integration is dx dy, and that means that in letter C, you need to have it written as dy dx. Now, do we need to switch the order of integration? Not really. This problem, I mean, we were able to integrate just fine without switching the order, but I'm just trying to get your skill of being able to switch the order practiced, because you will need to have that skill ready to go when it's going to be your time. So then how do we do the order of integration dy dx? Well, this is the vertically simple choice for order of integration. So if I were to do the representative rectangle, or in my case, my little man, oh my God, I don't even think I can draw a little man that tiny. There's my little man. X is going to go from what to what? So what is the X doing on that region? What constant to what constant?
1 to 0.
Okay, but what's the lower limit?
0 to 1.
Yeah, you have to 0 to 1. 0 to 1, and because this intersection point is indeed the point 1, 1, and you could prove that analytically, of course, and you might need to at times. And now, using my little man, who's super tiny and sitting in that little sliver of a region, his head is touching what? Is it touching the parabola or the cubic function?
Touching the parabola.
Mm-hmm. And so would I put y squared here?
No.
No, that's bad. You need to have a variable that isn't a y, because we're integrating with respect to y. So you need to do some scratch over on the side, and your scratch would be, okay, you need to rewrite x equals y squared and solve it for y. So if you square root both sides, you're going to get that plus or minus again, but we're going to take the plus. So you're going to have square root of x. And then his feet are sitting on the cubic, but you don't want to put, cube root of y here. That would be bad. No. So you're going to look at x equals cube root of y and solve that for y. And then if you raise both sides to a power of 3, you'll have y is equal to x cubed. And so that's going to be the lower limit. Ooh, boy, this is not doing too good when I use my eraser. Hang on. Okay, there we go. So we've got we've got square root of x up here, and we have x cubed down here. And if you did this integration correctly, you integrate 1 with respect to y, so you get y, where y goes from a lower limit of x cubed to an upper limit of square root of x. And then you're going to integrate with respect to x. So you have your dx going there. And then you end up with a calculus 1 problem near the very end here. And hopefully everybody was able to do this. and you should have gotten 5/12 also. Okay, questions?
No, I'm good.
Okay, you feel like you're getting this a little bit?
Getting it a bit more.
Yeah. It feels like a review from Calc 1.
Yeah, it does, doesn't it?
Mm-hmm.
Now, switching the order is super important, and when you take a quiz on this stuff, way after the midterm, in like a week and a half, believe me, I'm going to be asking you to switch the order. So it's important you have that skill, and it's really fun. It's not too hard. I mean, it doesn't take as much time as, say, trying to do a Lagrange multiple problem. Okay, now sometimes the region gets a little bit tricky, and just like Calc 1, because you had to do this in Calc 1, trust me. I think I even give the same exact problem in my Calc 1 lecture. You might have to subdivide the region into subregions so that you can figure it out when you're going to do the total area. So what do I mean? Check out this graph, 4x minus x squared, and that turns out to be, hopefully I can draw this pretty well, an upside down parabola like that. And then when you graph the straight line, negative 3x plus 6, well, 6 is way up here. That's the y-intercept. And it's going to turn out that 2 is the x-intercept. So that thing is going to come screaming down like that. So what is the area that is below the graph of the parabola, above the x-axis, and above the line, negative 3x plus 6? So if we fulfill all of that criteria, we're going to shade in that region there. So I hope that you can see that if we're going to represent this region using double integrals, or even if we were doing this as a Calculus 1 student, and we had to represent the area with single integrals, you would need more than one integral. Whether it's dy dx or dx dy. Did my microphone just go out again?
No, I hear
No,
you.
No,
you're
you're
still
good.
there.
Because I just got a little note here. Boy, am I having some problems. Is it my Microsoft Surface Pro? Who knows what it is? I can't figure it out. Okay. Well, just annoying. Very annoying. Okay, so the reason why is, let's say we're going to draw my little man in here. Can you see that if I draw the little man over here to the left of x equaling 2, he's going to have different limits than if I draw him over here to the right of x equals 2? Can you see that?
Yes.
Yeah, and so that's kind of an issue here. So you're going to actually want to cut this region into two sections, and I'm going to cut it right there, because to the left of that line, x equals 2, that's the line x equals 2, the limits for y are going to be this parabola and the straight line, but to the right of x equals 2, the limits will be the parabola and the x-axis. So that's why we have to cut this into two pieces. So the total area is going to equal, and I'll call the left-hand side region 1 and the right-hand side over here region 2, is going to be area of region 1. I've got such a delay here. I'm like writing in invisible ink. Oh my God, this is crazy. Well, you know, my 4th grade teacher prevented me from getting straight A's. Because when I was a kid, I was really into getting my straight A's, and then when I got to college, that ended. But so why did I get straight A's in 4th grade? Because my handwriting sucks. Yeah, she would give me like C's and D's in penmanship. I don't even think they grade 4th graders on handwriting anymore, do they? Now that they all have iPads?
They do.
They do?
Yeah, my daughter's in 3rd grade and she gets graded on her writing.
Oh, well, I hope she gets better scores than I.
I remember in like 2nd or 3rd grade, I was sent home almost every night with like one of those like fill in the blanks, so like trace the dotted lines for handwriting, because my handwriting was so miserable. Not that it's
Ooh.
improved in any substantive capacity, but it's
Right.
a funny story.
Yeah. So they give you like these little like connect the dots, and here's the letter A.
Yeah.
Something, and you're like,
Exactly.
oh, let's see. I don't know if I could stay in between the lines.
I never did.
Here's my H. How's that? How's that, Teach? Okay. All right, so the area of 1. Okay, let's take a look over here. how would we iterate this double integral representing the area of region 1? That's over here. So if I choose my favorite order of integration, dy dx, since I do have my man drawn vertically, x is going to go from what pure number to what pure number? Now you got to be careful, because I'm not sure if I know the interaction of those two graphs. I have to do your pre-calc stuff first. When does y equal y? When does 4x minus x squared equal negative 3x plus 6? And folks, this is a quadratic equation. You know how to solve it. Get everything on one side and 0 on the other, okay? And then if it factors, factor and use the ZPP. If it doesn't factor, and then go ahead and use your quadratic formula. Let's hope it doesn't get to that. I hate that quadratic formula. You know what I mean? I'm just saying. You can't. So now what? Kindergarten has iPads. Ooh, that's wrong. I'm sorry. When I was in kindergarten, we had finger painting, okay? Not iPads. All right, so now I claim this does factor nicely. Can you do this by inspection, folks? You getting good at factoring?
Yes.
-1, -6.
Okay, I'll buy it. Okay, and then the ZPP says if something times something is equal to 0, one of the other somethings is equal to 0, right? So you go, okay, x minus 1 equals 0, or x minus 6 equals 0. You should be pretty good at the ZPP after having gone through all that, finding relative maximums and minimums. So I get 2 answers, but which one am I going to use?
Left.
Yeah, because this is where x equals 1. They do eventually intersect way down here when x is equal to 6, but we don't care about that one. So we're going to have 1, 2, and then right where I slice my region is going to be the upper limit for x. And then the limits for y, if you look at my little man, he's standing here, the upper limit is going to be the 4x minus x squared, and the lower limit is going to be the straight line y equals negative 3x plus 6. Okay, there's region 1, and I'll let you figure that guy out. Plus, when we iterate the second region, his double integral, again, we'll keep dy dx as our favorite order of integration. X is obviously going from 0 to 4, because 4 was the x-intercept there for that parabola. And then y is going from a low, or the little man's feet, the x-axis, but that has the equation y equals what? What's the x-axis?
0. Y equals 0.
And then the upper limit, the little guy's head is on the parabola, which has the equation 4x minus x squared. Okay, so I'm just going to say etc. over here. You have to do that double integral, and then you go evaluate the other double integral, and then add the results. And I claim if you add the results, your final answer should be 15 halves. And that's the area of the total area there. Okay, so sometimes you have to cut your region up to get it to work. Question?
For the second term,
That's this guy here?
yeah, and for the outside limit.
Oh, sorry, it shouldn't be a 0, should it? My bad, that should be a 2. Thank you. Yep, oops. Try to do it too fast. Okay, so I'm pretty much done with today's lecture. So I'm going to stop the recording. If you need to stay and ask some last minute questions,